So, first I have to say that we are quite unfortunate to live in an age that is so hard to even survive. We're surrounded with numerous type of hazard events, such as like meteorological events, hydrological events, climatological events, and this is make us suffering quite a lot. For example, in the most recent 5 years, the average number of billion-dollar level natural disasters is 20.4 per year. And the figure shown in here is made by NOAA, demonstrating the billion-dollar level disasters in 2024. Sadly, because of policy and budget cut, this is perhaps the latest image we can get from NOAA. And there have been 24 confirmed billion-dollar level weather or climate disaster events in the United States. And these events resulted in the deaths of 418 people and have significant economic effects on the areas impacted. And these events come in a wide variety as well, namely tropical cyclones, wildfires, and winter storms. However, I think we are also living in an age of hope because the marriage of AI and geospatial data science provides powerful tools that empowers the integration of emerging multimodal big data, enabling smart environmental sensing, disaster management, intelligent resource allocation, and so on and so forth. And since climate resilience is quite a big topic, and I will narrow down the scope to GeoAI in disaster management. And I will show you how GeoAI can help alleviate human sufferings and promote community resilience during hazardous events. And after that, I'll follow it by briefly introducing my ongoing work and my future research. So first, let us take a look at one devastating event, Hurricane Harvey. Hurricane Harvey was a powerful Category 4 hurricane that made landfall on Texas Gulf Coast in August 2017. The storm caused an estimated of $125 billion in damage as the costless tropical cyclone in US history at the time. Thousands of homes and businesses were destroyed or severely damaged and result in at least 107 direct and indirect fatalities. Besides the wind damage, it is particularly noted for its unprecedented and catastrophic rainfall, which led to historical flooding. And the news report on the left actually shows the emerging conditions it caused in Tennessee. And in addition to the heavy flooding in the real world, in the virtual world, Hurricane Harvey made the social media platform flooded with rescue requests as well. So Harvey was one of the first events in which social media played crucial roles in fast response and rescue missions. For example, in Houston at the time, around 10,000 Houston residents were trapped in their homes or on their way to evacuate. And the local police department rescued only about 30% of them. Because at the time, the 9/11 system was overfloated and many Harvey victims turned to social media for assistance. Users post rescue requests and their addresses on social media, while volunteers and responding agencies search for those messages and send help. Here are several sample rescue requests from Twitter or X. For example, at Houston Police, my friend grandma is stuck in her attics, and the address followed by that. So at that time, harvesting these information was done manually most of the time, which is extremely labor intensive and inefficient. And in that situation, inefficiency could be a matter of life and death. So we're thinking, is it possible to design and tune a deep learning model to automate and expedite the process with sufficient accuracy? Actually, we believe so. But before our model design, we need to figure out how human beings make this decision. So how do we know if a sentence in a social media post is a rescue request or not? Well, for us, it's quite simple, just to decide if it's a rescue request. And this seems quite absurd because we're so familiar with this process that all the decision makings are happen subconsciously. However, if we think slowly and decompose the process, it is essentially a two-step approach which involves language understanding and categorizing. And lucky enough, computers tackle with this problem similarly. For the first part, understanding the language, we do have a counterpart in the natural language processing domain called language models. It can be as simple as a dictionary or as complicated as a huge neural network. And for the second part, categorization, deep neural networks have already done a pretty good job. Usually it is implemented by a linear classifier or a multi-layer perceptron. Therefore, our question had been decomposed to design and train a feasible language model and classifier combination that can accurately identify rescue requests. And when we take a look at the recent history of natural language processing, technology was developing fast during the past decades. This figure condenses 15 years worth of work into 8 milestones, and each single one of them lays solid foundation for the latter. And in 2018, the introduction of a variety of transformer models which benefit from the attention mechanism. You might or might not heard about it, but it is very famous architecture proposed in a paper named Attention is All You Need. And it pushed the performance of a language model to the next level. And one of them, the bidirectional encoder representation from transformers by Google, also known as BERT, has outperformed previous models, achieving the state-of-the-art performance at a time. And this is the milestone language model that pushed NLP to the next era, and that's why we decided to use BERT as our language model. And let's take a look at the model architecture we designed. The model in the blue rectangle is BERT, which consists of 12 transformer blocks, which is shown in the figure on the left. The transformer blocks are essentially arrays of stacked multi-head self-attention. I'm not going to detail the BERT architecture here. You can simply consider it as a huge chunk of neural network that contain hundreds of millions of parameters. And what does this chunk do is to turn the input sentence into several arrays of numbers, which we call embeddings. And these embeddings are supposed to capture the meanings of the input sentence and context information. And BERT per se is originally designed with a special input token, the CLS token, the purpose of which is to be used for downstream classification tasks. And the embedding output of the CLS token is supposed to capture the information of the entire sentence and can be followed by a simple linear classifier to make prediction. So we're thinking, how about we swap the linear classifier to a slightly more complicated multi-layer perceptron, which is shown in here, to see if it could lead to better results. And in addition to that, we designed 2 more architectures. The figure on the right shows another one. Instead of using the CLS embedding, we'll link all the output embedding with a long short-term memory neural network to make inferences. And the third design is the one we are most interested in. We think that we might still leave out some information by using only the condensed information from the output embedding of BERT. Therefore, we extract all the hidden layers from BERT to retain as much information as possible to form a hidden layer map. And we stack a convolutional neural network on it, which is usually good at extracting features and commonly used in image processing. And we follow the CNN with a linear classifier to render the results. We compare our model to some baseline models, and this table shows the language model we're comparing with. Some of them are earlier models, such as Glove and Elmo, and some of them are other transformer-based models. For example, Albert and the Stillbird are a simplified version of BERT with fewer parameters, but comparable performance. And Roberta and LXNet are more complicated, larger models, which supposed to have better performance. And this is the result of the comparison. These models are trained and tested on around 9,000 manually labeled tweets. And we can see from the figure here that all BERT-based models generally outperform the baseline models by approximately 10%. They even render better performance than those more complicated models. And BERT with a convolutional neural network performs the best with F1 score equals to 0.919. It is quite reliable performance for identifying rescue requests from social media data. And we call the model we designed Victim Finder, and it can be used as the backbone of future rescue missions. And this work was published in the Computers, Environment, and Urban Systems. It is one of the pioneering work that innovates the use of large language models and bring it to disaster management. It has also inspired numerous follow-up studies, including one of my own. Okay, let's get back to the case of providing rescue during Hurricane Harvey. The study I talked about just now can accurately identify help requests, but we still need to figure out the location of the help request before sending help. Let alone the geotag tweets made up only around 1% of all tweets. If we take a look at the rescue request samples, we'll notice that people requesting for help prompt to mention the address in the textual content rather than using geotags. So what if we can automatically extract this address information from the textual content and locate them on the map? It would drastically reduce the workload of the first responders. However, the performance of existing tools that handle this type of task is limited. Therefore, we decided to give a deeper dive with the knowledge we have in natural language processing. So to formalize the task we were talking about, we're actually dealing with a general geographic text called geoparsing, which can be represented by the web application shown on the left. So geoparsing contains two steps. First is called the toponym recognition, which extract address from texts, and followed by toponym resolution, which converts address to coordinates. And toponym resolution is also called geocoding, which is usually done by using available geocoding service, such as Google Geocoding and geocoding service provided by Texas A&M University. And in this study, we are only focusing on the first part. So toponym recognition is a subtask of name entity recognition that involves identifying and classifying named entities in text into predefined categories, such as person, organization, location, time, and so on and so forth. And in deep learning, it is a token level classification task where the input is a chunk of text, and every single word in the chunk is a token, and the output is a specific label assigned to each token. And this is the part we're trying to optimize by designing a novel deep learning model. Since we're geographers, we're quite familiar with the Tobler's first law of geography. Everything is related to everything else, but near things are more related than distant things. Well, this is quite obvious. I don't even know why this can be considered as a law, but it does form the foundation for a variety of geographic theories. And since words in location names are close to each other and comes in groups, in sentences or documents, we're considering taking advantage of this clustering feature and see if it could help to enhance the performance of toponym recognition. Similar ideas have been applied by scholars to detect patterns from remote sensing images to enhance the performance of crater detection. And in our case, this figure shows the architecture of the model we designed, and we named it TopoBERT. It is a plug-and-play toponym recognition module harnessing fine-tuned BERT. So in this case, BERT plays the role of language model, and we concatenate the embedding output of BERT to a one-dimension vector and apply several one-dimension convolutional neural network on it to extract the clustering feature. And then we follow by a regular max pooling layer and multi-layer perceptron to execute the token level classification. And a total number of 10 datasets were used in this study. They're listed in the table on the left. The first 3 datasets are used for training the model and tuning the hyperparameters, and the other 7 datasets are used to evaluate the performance. And we also compare our model to a list of strong baseline models, which are listed in the table on the right. The first 4, Stanford, NLP, Spacey, Flare, and NLOR, are general name entity recognition models or tools. And the Neuro TPR and Gaze PNE2 are exclusively designed for toponym recognition. And this giant table here shows the performance of the model across our dataset. So from the table, we can observe that each model has its unique character and performs differently on different datasets. The Stanford NER tend to render results with high precision but low recall, which means the majority of its positive predictions of the place names are correct. And Gaze PNE2 performs stably with similar precision and recall scores. And we can clearly see that our model, which is at a button, performed best across many datasets. It presents the highest recall score on 5 out of the 7 datasets we tested. And this indicates that TopoBird tend to be inclusive and good at identifying the majority of positive instances. The average score are computed among all the dataset to compare the general performance of the models. And in this case, Stanford NER has the highest precision score that equals to 0.863. And TopoBird prevail in both recall and F1 score with scores equal to 0.886 and 0.854. And this work was published in the International Journal of Digital Earth. The figure on the right demonstrates the location of tweets processed by TopoBird during Hurricane Irma. And this work can alleviate the challenge in geolocated social media data harvesting. And at the same time, it also provides solution to a general geographic problem, toponym recognition. It can be easily integrated to numerous tasks that requires extracting location information from texts. So the aforementioned 2 studies can significantly smoothen the rescue missions during hazardous events. And we plan to delve deeper by taking advantage of this precious location-based social media data we harvested and examining whether these spatial and temporal patterns, as well as the semantic element, can reflect the impact of disasters and benefit decision-making. Sorry. This was quite meaningful because based on existing literature, disaster damage report usually comes quite delayed, and it is hard to access the actual impact based on the only resilient indices. And social media data, in this case, can be a very good real-time agent to reflect disaster impact. And another novel part of this research is that we investigate 3 devastating hurricanes: Hurricane Harvey, Irma, and Ian. The reason behind it is that Hurricane Harvey and Ian both took place in 2017 at almost the same time, and Hurricane Irma and Ian both made landfall on Florida. It could be interesting to see if there will be any specific patterns due to these attributes. So the data we use is primarily social media data we have, and after scrutinizing the data we collected, we noticed that there are 4 major types of posts that are highly relevant to human response to disaster impacts. So the first one is the rescue request, as I mentioned in our first study. And there are also people requesting help for their animals or reporting lost animals. And there are also a large chunk of social media data that has information about infrastructure malfunction. And there are also people offering help and shelter information on social media platforms. So we decided to take advantage of these four categories of social media data. And to identify it, we're still using the deep learning classifiers. And this is the workflow of this study. First, we collect the raw data using Twitter developer API, and we use a deep learning model to classify the tweets and also extract location information from the tweets. And then we perform a series of spatial analysis based on the data we have. So in this research, we tend to answer three research questions. The first one is, can tweets be categorized into fine-grained topics with deep learning models? The second is that what are the spatial and temporal patterns of tweets during these three selected hurricanes? And third is that, can indices derived from tweets under fine-grained topics be an auxiliary data source to better assess disaster damage at county level? For the model part, we're basically using it to categorize Twitter into four classes. And we're following the structure we use for the victim finder. And instead of using a binary classifier, we swap it into a multi-class classification test. And this table shows the performance of the model. The result based on the testing data set is shown in these orange columns. And the performance is quite good. However, we are worried about the performance since the training data set is not evenly distributed. A large portion of the data belongs to the not related class. So we feel fear that the model will like blindly infer that the class belongs to the not related class. So we also manually validate the performance after we applied our model to the whole data set. The manual validation results are shown in the gray columns, and they're surprisingly good. The App1 scores are all nearly above 0.92. And we also manually validating the geoparsing result, and the accuracy is also quite high. It's around 92.6%. So at this point, we are confident enough to say that our model can do a good job classifying all those trees and extract location information from them. And then let's take a look at the temporal patterns of the fine-grained social media data first. The y-axis in this figures is the number of tweets, and the x-axis is the time. And the dashed line in the four different colors represent the four fine-grained topics we talk about, and the blue solid line represents the total number of tweets. And we pair them with the power outage data, which is represented by the red solid line. The vertical dashed line indicates the time when the hurricane made landfall. And we observed that the numbers surged around 2 days after the landfall, and there are way more infrastructure-related tweets during Hurricane Irma and Ian than Harvey. One interesting pattern is that for Hurricane Irma and Ian, the number of disaster-related tweets decrease and dwindle with the number of power outage, but for Hurricane Harvey, the number of power outage remain high for a period of time after the number of tweets diminished. This can be explained by the fact that Harvey caused a lot of flooding, and the power outage during Hurricane Harvey was caused by inundated power plants or substations, which took longer to recover. And then let us take a look at the spatial patterns. This figure shows the spatial distribution of the disaster-related tweets during the Hurricane Harvey under fine-grained topics. These figures just provide an intuitive sense of where those tweets are. And to further evaluate the impact, we need to normalize the number of tweets by population at county level. And we call the normalized number of disaster-related social media data the DSI, which is disaster-related social media indices. And the figure shows the DSI across 3 hurricanes. The row indicates the type of DSI, and the columns indicate hurricanes. And the top 3 counties with the highest DSI are labeled in each subfigure. And let us take a closer look at two of them. So simply by eyeballing them, we observe that across three hurricanes, the infrastructural function related tweets cluster around the hurricane track, but the help requests exhibit different patterns. For Hurricane Harvey, the counties that exhibit the most intense help requests were not so close to the track, but in the severe flooded areas, according to reports. And this might indicate that rescue requests from Hurricane Harvey are largely due to flooding. And for Hurricane Irma, Maroon and Polk County lies on the track of hurricane, but St. Louis County is a little further away from the track. And referring to the rainfall animation of Irma, which is shown on the left, we can see that the St. Louis County experienced heavy rainfall and caused flooding, which result in this strong signal of help request. And for Ian, the spatial patterns of help request and infrastructural function posts are quite similar. And this indicates severe wind might be the major cause of damage during Ian. So following that, we're trying to use different variables to predict disaster damage. To make sure we're on the same page, but this study attempts to investigate what are the most influential factors and how well the assessment can be when we use some socioeconomic factors, some geographic factors, and adding some disaster-related social media indices were designed to assess disaster damage, which is represented by the number of insurance claims at county level. Referring to existing literature, these 10 socioeconomic factors are selected. They include the young population, education level, income, urban land coverage, percentage of female household, percentage of mobile homes, available phone service, property level vehicle coverage, and employment rate. And four geographical factors are selected to mimic the impact caused by the hurricane. They are threat level, which is essentially the kernel density estimation based on the track of the hurricane, as well as the intensity of the wind along the track. And three distance-based metrics, namely the distance to the hurricane track, distance to the landfall point, and distance to the coastline. And the color density of these figures are actually quite intuitive. However, in the real world, there are uncertainties. Things do not always happen the way we expected. And that is the reason why we also try to incorporate disaster-related social media indices. So we first run a simple experiment to calculate the correlation between the social media indices to disaster damage. The results are shown in this table. We can see that there are positive correlation between the total number of tweets to disaster damage for Hurricane Harvey and Irma, and high correlation between infrastructure-related tweets to damage across all three hurricanes. And this indicates that DSIs can be a good resource for predict damage. And in order to figure out which independent variable has higher impact to disaster damage prediction, we conduct the following regression analysis among all variables we mentioned. But before the actual regression analysis, we conduct a multicollinearity test to exclude the variables that are highly correlated with each other, since we're talking about a really great number of variables here. And the correlation threshold is set to 0.7, and the selection of variables are based on a lower AIC score in a series of step regression analysis. And this is the table shows the independent variables that are excluded from the final regression analysis. And this table shows the result of the regression analysis. In the case of Hurricane Harvey, when using only the socioeconomic factors in the analysis, the adjusted R square is only 0.06, which is quite low. And after appending the geographical factors, the performance enhanced and achieved an adjusted R square of 0.26. But when the social media indices are added to the analysis, the adjusted R-square reached 0.809, which is significantly higher than the two previous experiments. And this indicates that adding the fine-grained social media data can improve disaster estimation. But for Hurricane Irma and Ian, we only observed a boost of performance when adding the geographical factors, and the performance barely changed when adding the social media indices. And this pattern can also be explained by the fact that during Hurricane Harvey, the major cause of damage came from flooding, which can be properly represented by social media posts, especially help requests. And the damage from the Irma and Ian are more likely to be direct wind damage from the hurricane. Therefore, the geographical factors become proper representative that help better damage estimation. So, after a series of spatial, temporal, and regression analysis, we came up with some take-home messages. First, the spatial temporal patterns can reveal the unique characters of the hurricanes. And the DSIs, the social media index, can be a good indicator to estimate disaster damage, especially for the ones that are not directly caused by wind. And this work strengthens the usability and potential of social media in disaster response and advocates that social media data vendors enhance the accessibility of data in a privacy-preserving manner. Okay, and following my train of thought on using spatial big data to assess disaster damage, we expand our data source from VGI data to visual data. To be more specific, street view images. Numerous existing studies have attempted to leverage Google Street View to estimate disaster damage. However, there are two major gaps. The first gap is most of the studies focus only on post-disaster imagery. Few studies incorporate pre-disaster imagery, and pre-disaster images is actually quite easy to obtain. And we believe that adding pre-disaster imagery as reference can help enhance the performance of disaster prediction. And the second gap is that most work relies heavily on labeling the post-disaster imagery. And we try to find solutions to alleviate this labor-intensive procedure. And the objective of this study is threefold. The first is to assess the performance gains of incorporating pre-disaster street view images in fine-tuning deep learning models for disaster estimation. And second is to design and evaluate a dual-channel neural network model that integrate pre- and post-disaster street view image for disaster assessment. And lastly, to investigate the feasibility of leveraging multimodal large language models in disaster damage estimation, risk perception, and damage detection across bitemporal images. So the data we collected for this study is from a Pillory. There are 2,610 pre-disaster street view images captured on August 29, 2013, and 3,246 post-disaster street view images taken on October 17, 2024. So we're examining the damage caused by Hurricane Helene. And these images are paired based on their coordinates. And the post-disaster images are manually labeled into three classes. This is there's a total number of 555 mild damage post-disaster images, 1,088 in moderate damage category, and 606 in severe damage category. And the deep learning model we use in this study are convex and swing transformer. Well, usually there are two ways to perceive an image: to have an overarching view by looking at the whole picture, or looking at a segment of the image and paying more attention to the details. The rationale behind the selection of this model is that we want to test whether how we look at images matters or not. The convex is based on CNN and focuses more on the general appearance of the image, while the swim transformer is structured on transformer blocks and apply a sliding window approach. And this model focuses more on the details of the image. And we experimented both the tiny and base version of the models. Since we're taking advantage of using pre-disaster and post-disaster images, we designed a dual channel approach. And this figure demonstrates the workflow of it. The pre-disaster images and post-disaster images are fed to separate models and get their vector representation. The vector representation are then concatenated and followed by fully connected layer to make prediction. This figure shows our core experiment results. The radar image on the left is the training result without the pre-disaster images, and the right is the dual channel approach with the pre-disaster images. We observe that adding the pre-disaster images can significantly improve the disaster perception ability of the pre-trained model, especially for the mild category. And another thing we try to do in this study is to use GPT-4o to label the images for us. This figure shows the prompt we're using. Essentially, we provide clear instructions of what we want the model to do in natural language, defining 3 categories we want the models to identify, and provide constraints to the output format. And based on the result we have at the moment, GPT-4o can properly describe the image in a logical and reasonable way, sometimes better than humans do, and can provide reasonable accurate scores for each output scores we specify. But the labeling result is quite different from our manually labeled results. We observed a systematic error of large language models, and it tends to mistakenly label the moderate classes as the severe classes. And our future work will continue to investigate this part. And some quick take-home messages for this work. First is that the pre-disaster street view image can enhance the performance of disaster damage estimation by around 10%. And swim transformer exhibit better performance compared to convex models. And the multimodal LLMs have the potential of being used for data labeling. And this work is now impressed by the computer's environment and urban systems. Well, I would also like to talk about the impact of the aforementioned work. So disaster resilience is a subset of climate resilience, which can be regarded as the ability that community have to bounce back to their original state, or even better than the original state, after being struck by disasters. And it is highly related to the 4th phase of disaster management, namely response, recovery, mitigation, and preparedness. The aforementioned 4 studies have profound impact on them by bringing direct benefits to the response and recovery phase, and the knowledge we learned from analyzing the data can inform future disaster management in the mitigation and preparedness phase. Well, that's a brief introduction of the 4 previous studies, and now I'll briefly mention my ongoing work and future work. So my research focused on advancing the theory and methodology of geospatial data science and applies the theoretical and mathematical innovations to facilitate climate resilience. Well, this might seem quite vague, and let me elaborate on this by adding more details. So theory-wise, we consider the ethical issues arising from the intense use of deep learning algorithm tools and geospatial big data, and proposed a novel concept called responsible GI science. Well, the responsible GI science refers to, based on our perception, conducting geoscience research or developing geospatial technologies which strictly adhere to a set of rules and address ethical principles, account for human values, and safeguard societal interest. And under this concept, we propose 4 paradigms. namely security, trustworthiness, equity, and philanthropy. And under each paradigms, there's a list of subtopics being discussed. And this work is under second round of review by the International Journal of Geographic Information Science. And for the methodology part, in addition to adding various data sources such as remote sensing, human mobility, Internet of Things, built environment, and survey data, we also attempt to innovate the AI algorithms. Well, AI agent is a hot topic at the moment, and we think building our own Geo AI agent could be a one place to go. And in addition to that, foundation models can be the core of all AI agent. And in our geographic domain, I think the development of geospatial foundation models is a crucial part of GeoAI. And my first step is to try to understand current LLM's capabilities in fundamental geospatial tasks, and also trying to apply geospatial thinking in the design of foundation models. And application-wise, besides disaster, I have already conducted study on infectious disease and extreme heat and their influence on human mobility. And also I'm exploring the public health domain by examining the environmental factors on public health in terms of mental health and dementia. And more work will be coming, so please stay tuned. All right, I think that's all for my presentation. Thank you so much, and questions are welcomed.